Okay, well, welcome everybody to this farm video. My name is Robin Grieve, and farm, of course, stands for Facts About Ruminant Methane. We're an organisation which is passionate about getting the truth, the scientific truth about the impact of methane emissions. And I'd like to welcome our Chief Executive, Owen Jennings, to introduce our speaker.
Well, thanks, Robin, and it's a real privilege to be able to introduce to you Professor Dr Geoff Duffy. Geoff's an internationally acclaimed chemical engineer, and he's been a consultant worldwide over a range of industries and activities. He's got numerous practical innovations, and he's developed many novel processes, some of which are still endorsed today and are used by industry right up until now. He's taught fluid mechanics, heat transfer, and specializing in radiation and automatic control for some 4 decades. And he's given hundreds of presentations around the world on a very wide range of topics. His research has been published in over 250 publications. He's received top awards internationally, and he was the first in Australasia to receive the earned Doctor of Engineering degree for pioneering research after his PhD. He was made a Fellow of the Royal Society over 30 years ago and the first chemical engineer in New Zealand to do so. Geoff's got a great grasp of the issues around greenhouse gases, and especially the dominant water vapour, which he will be emphasising tonight. And his views on that are widely respected around the world. We're indebted to you, Geoff, for giving us your time. The screen is yours.
Greetings, everyone, and thank you, Owen, for the very warm welcome. And I would like to just say thank you for joining us today. The topic, of course, as you know, is what is really causing weather change, and particular emphasis is on the role of methane, although what I'm going to talk about today applies to all greenhouse gases. So what's really causing it? It's going to be a practical presentation. There are no equations, no models, no ideas that are outside the realm of normal everyday thinking. It's facts-based, evidence-based, data from the web, and the references are available to you later on. We have a few handout type sheets that we can get to you. So I'd like to start with an overview first. The background. The background, there is a difference between weather and climate. I'd like to clear that up first. And then incoming solar energy is different from outgoing radiant energy from the Earth. Everything radiates, but we get radiation from the Earth and from the sun. We'll talk on greenhouse gases, the quantity or amount of each one, and then we'll look at radiation absorption as well as emitting potential of each of the greenhouse gases. And then we'll examine many other vital weather mechanisms, because there are a lot more, and we'll examine the real issues causing weather change, and finally give a summary and some goals as well. Well, setting the scene so we're all on the same page. Weather is the first thing we want to talk about. It's always changing. It changes hourly, daily, overnight, weekly, seasonally, and annually. So to be fair, that's straightforward. However, it is not just temperature change. In the newspapers and on the media, all you hear is this temperature change. And the mantra is 1 degree rise in 100 years. The world is going into a bad phase if we go more than 1 degree rise in 100 years. Well, that's a little bit unwise to say that, because each day it goes up 5 degrees, 10 degrees in the morning, goes down 5 or 10 in the afternoon. And if we walk from our veranda or under a tree out into the sun, we immediately get a boost of 5 degrees. So it's very difficult to say that a 1 degree has any great effect on our conditions and our living and the future of the world. But to be fair, weather is not just temperature. So weather includes precipitation, that's rain, hail, snow, etc. It includes wind speed and direction, and it includes humidity, and storms and other factors, meteorological factors. That's weather. So we must see weather is the thing that's changing. If we take the second one, climate change, and want to highlight that it's generally regarded as a regional thing. If you fly to Sydney and find the temperature, the rainfall, whatever it may be in a particular month, that will dictate whether you want to go there or not. But it's really a 20 to 50 year or so average of weather factors, meteorological factors that we mentioned. So it is really a mathematical average. And if it's a mathematical average, climate cannot cause anything, as we hear on the news. Climate is causing this, climate is, or it can't. It's only a mathematical average. In fact, climate itself technically does not exist. It is an average of weather. It's a mathematical expression. Now, there's no greenhouse gas. A greenhouse is what we know we grow plants in, has a roof and walls. Nowhere in the world is there a greenhouse. But the greenhouse gas concept is meaning that the gas absorbs radiation, and we'll explain that shortly, and it also emits it. It cannot store it, and it cannot trap it, as you see even on NASA, some of the old NASA sites talking about trapping. On the air, you'll hear this trapping of heat. Well, if the clouds trap heat, they'd disappear. They'd warm up and go away. So that's a false concept. And also, we'd like to talk about the fact that there's more than just radiation. There are winds and storms and rain and ocean mixing and stirring, waves and so on, all affect weather. And finally, just to say, global warming does not exist. The whole globe is not warming. Parts are going up, parts are going down. We may use an average temperature for the year or for the month that it's going up, but that's not has no significant meaning. So let's start with solar radiation. The hot gases around the sun are over 5,000 degrees and they emit radiation. It's called electromagnetic radiation. Now, just in case you're worried, its visible light is electromagnetic radiation, ultraviolet light, infrared, and you know, gamma rays, X-rays, and all these things are we know about electromagnetic radiation. Now, all this energy coming to the Earth comes 150 million kilometers through outer space, and it's absolutely cold. In fact, it's minus 273 degrees, and it's at zero pressure. So it's absolute vacuum, and it does nothing at all. There's no heating outside, and unless there's something out there like a spaceship gets hit by radiation, but no heating at all in outer space. Okay, so far we've seen what is actually happening. Does nothing at all in outer space, but we know that ultraviolet, visible, and infrared energy are the three main ones that we'll be concerned about in our talk today. Now, above where the planes fly, that's 15 to 50 kilometers up, we find that there's some bad UV, ultraviolet. Now, this ultraviolet converts oxygen into ozone. If it didn't, it would probably end up killing us on Earth. It's UVB and UVC. UVA is not too bad, but it causes little black spots on our face and hands and so on with time. It attacks biological materials. But fortunately, the bad UV is used up. Now, let's go to where we live. Where we live in the first 10 or 12 or so kilometers is called the troposphere, and it contains, that's where planes fly, but it contains about 80% of all the air that we have, and it contains nitrogen, oxygen, and argon. In fact, it's almost 99% of those three gases, 98.8 in New Zealand. But the radiation does nothing with nitrogen, oxygen, and argon. So it's so important to see that there's no direct radiation effects coming from the sun in space, and nothing when it gets to Earth with those three gases. Now, notice I underline direct. We'll see shortly that it has a secondary effect, but no direct effect by radiation. Okay, back with our atmosphere again. We've got a feeling for that. Now we must add water vapor and clouds, because that now makes the extra 1%, makes 99.8%, almost 100% of the atmosphere is nitrogen, oxygen, argon, and water vapor, including the cloud droplets. So these are the top four, and you see from here that water vapor is now number 3. In New Zealand, it's greater than argon. If we go to the tropics, of course, it's far greater than argon, but in some places, argon takes number 3. But notice I've put it as yellow, and the why it's in yellow, it is a greenhouse gas. That means it absorbs some bands of radiation and emits it, but the other 3 do not. So then what's next? Well, we've got the top 4, and then the others are carbon dioxide, and that's not 95% natural. And we've got methane, and that's at 40 to 50% natural. So carbon dioxide, there's not much man-made carbon dioxide in the air, and there's only a small amount of methane in the air. And we'll see this as we go along. So the top 6 gases in the atmosphere are listed there, and the yellow ones are simply to show that they're greenhouse gases. They absorb and emit radiation. Okay, now let's look at greenhouse gases by themselves. Let's just isolate them for a moment. Now, let's look first of all at the relative amounts. Water vapor, number 1, greenhouse gas is 1% in New Zealand. It's probably 1.5% in Australia and parts of New Zealand, wet parts, and 4% in the tropics up at Singapore. Carbon dioxide is number 5, and it's 0.041%. And methane is number 6, and it's 0.0019%, not very much. Now, to make this kind of meaningful for us as we walk around ourselves, let's examine it in the point of view. I've just picked a big city and used Auckland population of 1.7 million. What does that mean? Well, 1% is 17,000 people, 0.041% is 700 people, and methane at that very low percentage is 3 people. So the question we must ask ourselves, how does 3 in 1.7 million cause a lot of trouble in weather change? Now, it's illogical, totally illogical, and there's so few of them. Now, water vapor is 5,000 times or more greater than methane, and methane is 220 times approximately greater than methane. So that puts us into a better picture that methane is very small. It's almost inconsequential by concentration. So just repeating then what we've had, water vapor is 96% of all the greenhouse gases, 94% carbon dioxide is only 4%, methane and nitrous oxide percentages of the greenhouse gases, these figures are. So, you know, water vapor is not clearly number 1, and methane is clearly very small. And those 2 together, carbon dioxide and water vapor, make up 99.98% of the greenhouse gases. That's almost 100%. So you can see that methane itself is minuscule. So what is unique as we think about this? Well, water vapor gas is unique. It's the only gas that condenses. This is so vital. It's the only gas. It forms cloud droplets, rain, mists, fogs, and sleet. So it condenses. Carbon dioxide doesn't do it. Methane doesn't do it. And it's the only gas that freezes. So it can form ice crystals in high clouds or in snow or in hail. So we now have water vapor is vital because it can now change of state to liquid and solid. Now, the changes when you move from a liquid, you know, to boil a jug of hot water, how much energy you've got to boil to make it into steam, to make the whole lot into steam. The energy changes are enormous. The concentration changes are also enormous. And droplet sizes are enormous. And so are the crystal sizes when they change. And then, of course, when you go away from just particles or droplets, you've got to talk about population. It's a population phenomenon. And these are very large. Okay, now you may be a bit worried when we're talking about, not talking about methane all the time, but we need to put methane into its setting. 2/3 of the world is covered by clouds, and over 2/3 is ocean. So we now have water doing things that we don't normally, not often taught, even in school or even in university classes sometimes. But one of the biggest things in the world today is evaporation. 423 million tons, metric tons, evaporate and condense and precipitate down as rain every year. 423 million. That's 423 trillion tons a year. What does that mean? It's 13 million tons a second, 13 million metric tons a second. Now, once it gets into the air, the humidification. Now, I'd like to spend on that because I spend a lot of time and not too many people, a lot of research time on this. A lot of people don't understand humidification. The temperature can go down and the humidity can go up. That's exactly opposite of what you'd expect. The temperature can go down and your relative humidity go down too. But that can't deal with that tonight or today. So we have condensation. And now once we form droplets, we've got to move to talking about population, the numbers of these particles. They do agglomerate. And just to give you some idea, 1 billion trillion cloud droplets amalgamate or combine per second. 1 billion trillion, that is, a billion is a million. 1 million million cloud droplets combine every second. That's actually more than 4 times the surface area of the Earth per hour, if you'd like to calculate the surface area phenomenon. Then it precipitates. Now, this is important because if you get nothing else out of what we've talked about so far and tonight or today as we talk about this, the more the world heats up for any reason whatsoever, any reason, more water will evaporate. When more water evaporates, we have then an umbrella shield across the top. We get cooler immediately once a cloud comes. The water then, more clouds will be more rain, more cooling of the air, more cooling of the land and cooling of the sea. So water, if you heat it up, if you heat the land up or sea up more, it will be self-compensating, self-regulating, self-buffering and self-correcting. Now, this is what the NASA and NIWA and others should be really talking about, the self-compensating power and of regulatory power of water vapor. Good example, hot day in a car, 25 degrees, starts to rain. Look, a few minutes later, it's down to 18 degrees. So there's a big change. And these are not 1 degree in 100 years. These are 6 or 7 degrees in 10 minutes. So the question is, why don't we all know that? Well, here's one reason why. If you do a Google search, you'll find and ask the question, what are the main greenhouse gases? You'll have a whole bunch of these pickies, but let's pick out number 22 and just amplify that one. It's the first one. You've got to get to number 22 before it mentions water vapor. And so 95% it says is water vapor, and then carbon dioxide is a small amount, and 1.4 and methane's tucked near that 1.4 is the rest. So anyone reading Google, finding out what's happening, are going to be put off. So school kids, teachers, people in the street, us. Now, if we go to number 35, it's the first one, the very first one that shows us water vapor and clouds. So you've got to go down to number 35 pictorial to find those clouds as well. If you take the early one, you can see this is what they say, 82% carbon dioxide and 9% methane. That's why the government wants to tax it, because that's what they view. They disregard water and water vapor. Okay, conclusions so far. Water vapor is dominant, maybe 100%. Water vapor is the only condensable gas. And then the ones that don't condense, all the other gases don't form droplets or particles. It's less than 0.05% of the atmosphere, 0.05. And to put it in real terms, it's 1 in 2,000 parts of the atmosphere. The quantity of methane is minuscule. It's 0.0019 compared to the 0.05. That's mainly carbon dioxide, the 0.05. And the big thing and a unique thing that only water does is phase change or change of state. And that's a key mechanism. So we have evaporation, humidification, condensation, agglomeration of droplets, finally precipitation. Now I want to give 2 clear pictures. One is a pictorial and the other one is a graphical thing. Now here are some pictures, 3 were taken over a period of a few minutes, 15 minutes. They're taken from our place, looking out over the Hauraki Gulf. This fog came in very quickly. It's not windy, as you can see. It's not really windy. This fog came in and sat there for a while and then dissipated out and went out by itself. It was 23 degrees. There was 100% relative humidity because it's saturated. There was 20,000 tons of water per cubic kilometre. So it's pretty big, high and wide and long. And it was on the 7th of November, 2019 at 1:30 in the afternoon. Example number 2 is quite startling. For only a half a degree temperature increase, there is more water vapour produced by a half a degree temperature rise than the total increase in carbon dioxide over 100 years. That's 110 parts per million in 100 years. Just repeat that. More water vapour is added to the atmosphere by a half a degree temperature rise, and we've all been outside when there's been more than half a degree rise, than the total 100-year increase of carbon dioxide. Now, these data, you can get into these data for yourself on the web. I've picked this one, 10 to 10.5, kept the relative humidity constant, 118 parts per million, already larger than carbon dioxide. If you go 18 to 18.5, it's 197, which is almost twice the amount of carbon dioxide. If we go 25 to 25.5, it's almost 3 times the amount of carbon dioxide in half a degree if you're going from 20 to 25. So what can we say? Water dominates over carbon dioxide. And here is the rub. If water dominates over carbon dioxide, it kills, absolutely kills the meaning of methane in the atmosphere, because water swamps carbon dioxide. So imagine what it does in 1/10 of a degree. And it's important to see that. Now, the key word here is Lentech. You go on the Lentech calculator and you can calculate any temperature you like, any range, any relative humidity, within reason, of course, and realistic, and you'll find that to be true. They're the 2 illustrations. So greenhouse gases, we must also look at the radiation. We've done mainly with concentration, but let's look at radiation. Only 56% of the radiation coming from the sun ever reaches the earth. It gets scattered and shifted around in the clouds and so on by snow and mountains and so on. Only 56%. And it comes out of the amount that reaches the earth. 44% is visible, 48% visible light, 48% is infrared energy, and only 8% is ultraviolet. Now, visible light, we all know, or we call it white light, but if you put it through a prism, you'll get the colors: red, orange, yellow, green, blue, and indigo violet. You'll see that in a rainbow. We picked it up with our eye, and so a visible light: red, orange, yellow, green, blue, indigo, violet. Now, just near red, you'll see there's infrared. So just a little way from what our eyes can pick up, there's infrared. We don't have eyes in our head for that, but I should highlight that the end of all our nerve endings are infrared eyes that pick up. That's why we feel warm when we go outside. Now, on the other end, the more powerful end, the blue end, we get ultraviolet. And of course, the ultraviolet is the one that causes the spots. And that's why we put sunburn cream on. That's why we wear sunglasses, because the ultraviolet damages the eyes and also the skin. Okay, so 2/3 of the world is cloud, 2/3 ocean. Water is dominant, and water, clouds, and water vapor gas, water vapor is a gas, are the key and major ones in terms of radiation. Now, let's prove that. Now, this is taken from the web as well. It's modified just to make it look good for you, but the data is actually on the web. If we take the wavelength, that's like, and I'll explain that as we do it in a minute, coming from the sun, it's about 0.2 through to 3 micrometers. That's the wavelength. Now, the visible light is red, orange, yellow, green, blue, and indigo, and violet, and it's in the 0.7 down to about 0.3 range. That's what's the meaning of wavelength. That's so red has that wavelength in that range. Now, the other part is infrared, and that's infrared radiation. So let's look at each one. Well, let's look at solar radiation coming in. This is 100% solar absorption, and down the bottom is 0% solar absorption. So if we take carbon dioxide, we see that carbon dioxide has one at 100% and one at about 60%, but only in two spots, just like you only have several ranges, only a range there and a range there. So let's look at methane. Very small amount it can absorb, and it only absorbs in that range. Let's look at nitrous oxide. Well, it's extremely small, narrow range, a little bit more than they can absorb. But now let's look at water vapor. And so water vapor swamps radiation coming in. It's got 300% and 2 over 60 or 70%. And it operates over a greater range, and each one of them fatter. That green one underneath there is totally covered. And this one has got a little bit, so it can do something. So what have we got? We've got total domination of water vapor from incoming radiation. And what have we got from methane? You can just see a smidgen of methane there. And so methane has virtually no effect on incoming radiation. And these data are from the web. They're not from a research paper. That's published stuff that everyone can get hold of. And the reference is there, and we can supply that to you if you want to do it yourself, find it out. Now the Earth heats up and it radiates too, day and night. It reflects during the day as well as radiates. And at night, you know what, if you walk on hot sand, at night it's still warm and it gets colder and colder because it's radiating away, as well as some of the air is being warmed by it. So we have a different wavelength now. It's a 3 to 70. The other one was 0.2 to 3. Now we're 3 to 70, and it's a different type of radiation, but it's all infrared. There's no visible. It's all infrared radiation. Now carbon dioxide now has 2 bands, and they're wider and they're bigger. That's great. Methane, it's got 2 now, bigger and wider, but still don't get up to above, that's about 60% absorption level. Can't absorb more than 60%. And there's not much of it, so it doesn't absorb much. Nitrous oxide, it's not much stronger, but again, it's minuscule. It's very small. Now let's look at water vapor. And you can see again, it dominates, it swamps. A couple of greenhouse effects, greenhouse gas effects from carbon dioxide and radiation from Earth. Methane, I can't see it. There's a bit of nitrous oxide there, but you'll find that methane's no longer there. There it is there, and it's covered up by water. Water is a higher concentration, and it'll dominate again. So water dominates again, and methane's contribution is minute because it's almost zero, because water vapor covers it up. Okay, if we're happy so far with the effect of radiation, I just want to highlight before we finish, there are some other things that we must be concerned with. The Earth is rotating around its axis. In fact, you're sitting there now or standing there, you're moving at 460 meters a second. That's how we're rotating around the Earth, on our axis. There's also the Earth is revolving around the sun. It is not on a circular orbit, but it's on an elliptical orbit. So we get effects of the seasons on that as well. The clouds also, as we've already seen, exist, and they're not stationary at all, as you'll see from the next slide. We have typhoons, we have tornadoes, and we have storms, and we have hurricanes, and we have all sorts of massive movements of water, air circulating. And we also have lightning. We won't be able to talk about that today, but it's important as well. Then, of course, we've got the sea itself is active, and it's stirred up and mixing as well. And then we can have dry storms, dust storms in a town. But we have bigger things to think of that cause weather change, and that's sunspots, for example. Changes the magnetic field on the sun, but also it ejects particles as well. We haven't talked about solar wind, but that can be affected. Dark means there's not as much coming from that particular zone. And of course, here we've got solar flares. There's a solar flare there. So gas comes from the sun 350,000 miles up, and we get solid particles that come through the air as well, solar wind. But the Earth's rotating, so we get jet streams. And just recently, you know that the snow falls. It got very cold in Texas. So the cold air came down through Texas down here, and everything went the windmill stopped, the wind turbine stopped, nothing worked there, and they ran out of power, and it was a frigid time. Recently, you've seen the upflow from the tropics went through California here, and they got a heat wave right up into 100 degrees Fahrenheit, or 30 odd degrees up in Vancouver. That's caused by the jet stream. So we have massive air currents. We must consider those. You can't just consider radiation. We've got massive movements of liquid water, which are conveyor belts, and they're massive. Energy as well, and of course turbulence and mixing in both air and sea. So those last two slides are just to show there's far more than radiation. Sure, radiation is important, but we must add we've got conduction within a fluid and within a solid or liquid. We've got convection, as we've indicated, it's mixing in seas, and we've got hot air rising because it's warm air, moist air rises. We've got ocean currents and ocean big conveyors, and of course local disturbances on the surface between the liquid state and the gaseous state. We have waves. And we mentioned before, we have evaporation, humidification, condensation, and precipitation. Oh, it's a mistake there, precipitation. And this should be additional point, solidification, because some of the droplets go to ice. Now, they're all driven by differences, just as your power point, you have different 240 volts. We need a voltage driving force. We have temperature driving force to drive heat, concentration driving forces to drive liquid molecules or gas molecules or anything that's different, it'll drive it. Population with difference in droplets, small drops and big, there's a driving force due to population. There's driving force due to pressure. And if you're out on your tractor and that you're spraying, you know you need to build up pressure to force the liquid through. So we have pressure differences in air, density differences in air, and of course there are other things we haven't even mentioned so far. So there's more. We've got the geographical effects, mountains and valleys and rivers. We've got the coastal zones and inland. They're quite different because the coast is close to the water, inland is away from it. We've got the Earth's tilt. In fact, I was up in north in the Tropic of Cancer, had moved 200 meters in the last 50 years. Earth's rotation, and we've got Earth's precession, that is the axis is precessing as well of the Earth, and it's varying because we've got the moon wobbling, causing a little bit of wobble. The moon itself is wobbling us a bit, and if we didn't have a moon, we'd be totally wobbling all the time, and the North Pole would probably end up near New York some time. But the Earth's elliptical orbit is important, the Earth's magnetic field variations, because we've got a molten core. If we didn't have a molten core, we would die because the magnetic field deflects the radiant energy from the sun. We have the moon effects. We have tectonic plates, as you can see up in the little picky there, massive effects with active volcanoes under the water. 80% of all active volcanoes are underwater. We've got hydrothermal vents or fissures or cracks. We've got some melting ice melting from underneath, not just caused from melting at the top. At the bottom of South America, there's a fissure causing the sheets of ice to melt from underneath. And we've also got a hot equator and cold pole. So energy will transfer from the hot to the cold by convection, by movement of air to in that direction as it rotates. So what have we got then? We have people, all they're worried about is radiation and fossil, well, fuels, or maybe we could say fossil fuels. And of course, the other thing is they're worried about animals. What are animals doing? And you can see from the last 3 or 4 slides, there's a lot more happening than just radiation. We might ask the question, so what? Well, what's the real aim in New Zealand for reducing carbon dioxide and methane emissions? Well, it could be money, could be tax, could be control, could be power over people manipulating different things in the country. And it could be conformity, that we must conform to the world's push to change a lot of this stuff. Worldwide push to reduce combustible fuels. Now, the world's fuels, as we know, gas, oil and coal, still make up 80% of the total sources of energy for industry and power generation. And it's very likely in the medium to short term, it's going to be there for some time. It's been there for the last 40 years because population's growing. You've got to expand, and certainly the other methods cannot produce as much. So the emissions reductions are going to be limited, but we can improve the quality of what's being emitted. Renewables, solar, wind, possibly hydro, it's limited in cases, are all limited. And we've got tidal, possibly improve that a little bit. Hydrogen, they're looking into that again, even though that's a dangerous and a big problem. They have small potential. They won't overcome the 80% of the up in the world's fuels to produce electricity and run the industry. Of course, nuclear, they're going into new methods of small scale, more controllable nuclear plant, and that will be without any emissions. And that's got some potential because they're using thorium now as well. Once that comes online, the other things will disappear. So what are the real problems? Well, it's not farming, and it's not methane or carbon dioxide, and it's not fossil fuels, vehicles and industry, and it's not just radiation. But what we should be targeting is incomplete combustion, carbon particles in the air, other gases converted, sulfur plus oxygen forms sulfur dioxide, forms sulfur trioxide, forms sulfurous acid, forms sulfuric acid. That's where we got acid rain from in East Germany. So again, chemicals are vitally important. And the other thing is atmospheric pollution from solvents and other emissions that we should be controlling out of the atmosphere. Okay, conclusions. Methane's contribution is minuscule, it's minute. Radiation, water and water vapor dominate in the air. Water is the only fluid that changes state from gas to water to ice and back again. And clouds and macro mixing in air and oceans are also vital. We must be considering those. So that's the bigger picture. It's not too technical. That's just realistic and practical. So thanks very much for listening. And I hope you gained a little bit from that. And I'm open for any questions that you may have.
Thank you very much. Thank you very much to Geoff Duffy for their presentation. And thank you for watching. My name is Robin Grieve. I'm chairman of FARM, Facts About Ruminant Methane. You can see what we're doing on our website, www.farmemissions.co.nz.